continue about spanning trees, chapter 9, section 3. The section summary contains spanning trees, breadth first search, and depth first search. The section objectives include one objective, which is given a graph and a vertex or vertices, you will be able to construct a spanning tree of the graph rooted at a specific vertex using both a breadth first search and depth first search. Spanning trees. Well, the definition of the spanning trees: let G be a simple graph, and a spanning tree of G is a subgraph of G that is a tree containing every vertex of G. So basically, we have trees and we have spanning trees. Trees doesn't have or don't have simple circuits in it. And spanning trees is a subgraph of a given graph with no simple circuit. So what's the difference between them? If you can answer this question, you will have an extra credit for the next quiz. So given this example, find the spanning tree of this graph and how to construct it. First, this graph it's not, or it's connected, but is not a tree because contains simple circuits. You can see here between the edge that connects A and E, or the edge that connect E and F, or G and F. All these edges can cause a simple circuit. So in order to construct a spanning tree, we need to get rid of these simple circuits. So how? First, let's remove the edge between A and E. Okay, it's an extra edge. Then let's remove the edge between E and F. And finally, between C and G here. And at the end, we have the same graph as the original given graph, and all the vertices, but with no all the edges. So this is the main idea of the spanning tree. Just remember that the simple circuit, it's a path that has the same node at the beginning and at the end, but doesn't contain same or the same edge. We don't have the same edge appears more than once, or we don't have repeated vertices, in other words. Spanning trees, a simple graph is connected if and only if it has a spanning tree. We don't need to go over the proof again in this chapter. So how to construct spanning trees? So as you notice in the first example that I just removed the edges, but we cannot do that if we have like a big graph. We cannot examine or test all the edges that cause circuits or simple circuit. So there are two mechanisms or algorithms that enable us to construct a spanning tree from a given graph. The first one is called breadth first search. So we can construct a spanning tree using breadth first search. We first arbitrarily choose a root from the vertices of the graph. So in the exam or in the code, I'll give you this root. I will not let you choose an arbitrary root. So let's say we have a graph here. Okay, let's say we have a graph here that has node A connected to B, C, D, and D is connected to C. All right. So let's choose a root, and the root for this graph is A. This is the root. Okay. Now, then how to construct a spanning tree using breadth first search? First, we need to add all of the edges incident to the vertex, to the first vertex that we chose, which is the root. So A is connected to and C, right? And D. Okay? And we say that we test or we have visited the first level. So let me redraw it in terms of levels. A, okay, at level 0, and we have visited all the vertices or all the edges that are incident to A at the second level, which is level 1. This is level 0, B, B, and C, and this is level 1. Okay, for each vertex added the previous level, we add each edge incident to this vertex. So starting from B, is anything, is there any edge incident to B that we did not discover? A is discovered, so there is nothing. Now let's go to D. D, there is an edge. A, there is 2 edges incident to D that are connected to A and C, and both of them are discovered, so we don't need. And what else? See the same situation. So we have this final spanning tree that we have constructed using a breadth first search. So what's next? And we continue in this manner until all vertices have been added and we have a spanning tree. All right, let's have an example. So this is the pseudocode or the algorithm for breadth first search. It's out of the scope of this chapter, but if you want to have a clear idea or more details, you can go over it. But again, it's out of the scope of the. Okay, so use breadth first search to find a spanning tree for this graph. We have this graph, and again, we arbitrarily choose a vertex E, so it's not arbitrary here. Let's assume we have, we chose vertex E as a root. So this, starting constructing a spanning tree by drawing only the root E. This is first level, right? Now, we then add the edges from E or that incident to E, all the edges, and you can notice that there are multiple edges that are incident to E. What they are? Okay, let's draw it here. So we have E, and we have B, and next D. I'm trying to follow the graph here, but you can choose the first node is D, and then B, and then F, and then I, but I highly recommend to list them in order, especially if you have 1, 2, 3, so start like 1, 2, 3, not 3, 4, 6, and jump back to 0 or something like that. So what we have here, B, D, and then F, and then I. All right. Okay, this is level 1. This is level 0. Okay. And then, so we have discovered how many edges here. We have discovered E. We have discovered D, B, F, and I. And regarding to the algorithm, now we need to discover again from the discover the edges that are incident to the given vertex at the current level. So starting from the most left, which is B in this tree, don't start from D or F or C. Start always from the most left node. So now let's discover B. So what are the edges that are incident to B that are connected to the vertices that are not added to the our spanning tree? So B here is connected to A and C. Let's include them in the second level. It's A and C. All right. Okay, so let's remove them. So we don't need to visit them again. Okay, and how about D? Let's go to D. D is connected to A, but A is discovered already or have been visited, and also connected to H. Okay, so D is connected to only H. Let's remove H here on the graph. And what else we have? Now we have F. F is connected to C and J. C is already discovered or have been visited. So it's only F is connected to G and J. So F is connected to G and J. Okay. And now what we have here, we have finally C, right? This is I. Okay. Okay, this is I. So I, it's connected. Okay, now H. Where is H? Where's H? It's here. I is connected to K. Okay, so by now we have discovered the level 2. Okay, we have finished visiting level 2. Now let's go back and run the algorithm again on level 2, starting from A. So A, is there any incident or incident edges to node A? No, all of them have been visited. Also C, H, nothing. J, yes, or G, I'm sorry. G, there is only one incident edge that is that connects G to L. All right. So this node have been visited. All right. And what else we have? J here. All the edges have been discovered. And the last one, K. K is connected to N. Okay. And this level is level 3. And we have finished visiting all the vertices. And this is our final spanning tree. And if we need to continue, so we have L. L is not connected to any undiscovered vertices as well as M. So again, this is the spanning tree from this graph. Okay. breadth first search, there is another example. Use breadth first search to find a spanning tree for this graph. Choose vertex A as a root. So you need to construct a spanning tree for this graph, starting or choosing a vertex A as a root. Submit your solution, or you can share it by I'll create a discussion for this chapter on e-learning, so you can submit your solution and you can get an extra credits, and make sure to submit your solution by the end of the day or before the end of the day. And also there is another question or practice problem. Remove edges from the given graph to construct spanning tree using breadth first search algorithm with a vertex ordering. Choose vertex C to start, and maybe each of you will have different spanning tree, the edges especially, but that's fine since you are following the algorithm. And again, you can get an extra credit if you submit your solution before the end of the day. Another technique to construct a spanning tree is depth first search. So using depth first search to build a spanning tree for a connected simple graph, first arbitrarily choose a vertex of the graph as the root form a path. Form a path starting at this vertex by successfully adding vertices and edges, where each new edge is incident with the last vertex in the path, and a vertex not already in the path. Continue adding vertices and edges to this path as long as possible. So let's have a small graph just to have an idea about this search algorithm to construct a spanning tree. So let's have a graph, for example, let's say here A connected to B, connected to C. Let's have the same example. And D is connected to C. So form a path starting at a vertex that we have chosen, which is A. In this example, it's a root. So this is A. Okay. A, it's connected to B. Okay. A is connected to B. This is the first path. Adding vertices and edges, where each new edge is incident with the last vertex. So B is incident with the last vertex in the path, and a vertex not already in the path. Okay, so how about B now? Continue adding vertices and edges to this path as long as possible. So let's add the edges that are incident to B. There is no edges that are incident to B except A, but A is already discovered. So let's go back to A. Okay. Change the color. Okay. Now we are going back to A and discover other edges that are incident to A. So in this case, let's choose the right back. Let's come back. Okay. So now we are going back to A to repeat this the first step again. So from A, we have discovered B, and then what else? We have, let's say, C. Okay. Okay. From C, what we have? We have D. All right. And from D, we have two edges that are incident to D, which is A and C, but both of them are discovered. So this is the final spanning tree following the depth first search. So this is the algorithm. You can go over it, but it's out of the scope of this chapter. So an example here, use depth first search to find a spanning tree of this graph. Given the root of the first vertex, it's, I believe, yes, it's F. It's here. Okay, sorry about my email. Sound. So let's start with F. Here. Okay. So we build a path by adding an edge that connects the last vertex, which is F here. We have F. Now let's start. You can go to either direction. We have here 4 edges. You can choose only one at a time. So what we have here, we have D is connected to F, we have E, we have G, and we have H. So let's start with G, as is listed in this example, or as is provided. So this is G. Okay. From G, we can we have 2 edges that are incident to G. We have edge that connect G to F, which is discovered already, and we have H. So let's list H. Okay, and let's remove G and H. Okay, from H we have F, G, I, and K. So you can go either direction, but again, I'm following the solution that is provided here. H, so I'm going to K from H. Okay, and let's remove K because we have visited K. And then from K, okay, there is only one edge that incident to K from J. Okay, and let's remove J from the graph. Now we have reached this point at vertex J. Is there any edges that are incident to J that are or that we have not visited yet? No, it's only K. So let's go back. J. Now K. Is there any other edges that are incident to K and we have not visited yet? No. So let's go back to H. Again, the same question. Is there any incident edge that we haven't discovered? Yes, it's I. So from H, okay, we can add I. Okay, so this node have been visited. Now let's go back. I, because doesn't have any incident edges. Now let's go back to H. From H, is there any other incident edges that we haven't discovered yet? No. Let's go back to G, and from G to F, and from F we have E and D. And again, following this example, let's discover D. Okay, so let's remove D. Now we are at D node. So at D, is there any other instant edges to D that we haven't discovered? Yes, it's E. are at node E. E is connected to F, and C. F it's already have been already visited. So we have only D. Okay. From C, we have A or B. C is connected to A. Let's do something like that. Okay. Now we are at A node here. Okay. Is A connected to other undiscovered vertices? It's only C. So let's go back to C here. So from C, what is the next undiscovered vertex that is connected to C? It's only B. So this is our final spanning tree that we have constructed using depth first search. Practice problem. Remove edges from the given graph to construct spanning tree. Use depth first search algorithm with the vertex ordering. So here I'm giving you the vertex ordering so you can follow them to remove the edges and constructing the spanning tree that doesn't have a simple circuit. The second question, you have two graphs. You need to construct a spanning tree for each one. You can use whatever you want, like breadth search or depth search algorithm.